So here are a couple problems relating to sound level and intensity. The first question says, what is the decibel level of a sound that is twice as intense as a 90 decibel sound? And then it asks, what is the decibel level of a sound that is 1/5 as intense as a 90 decibel sound? So we should remember how the decibel or sound level is defined. All right, we use the Greek letter beta for sound level, and it's 10 decibels times a logarithm of the intensity of a sound divided by 10 to the minus 12 watts per square meter. Okay, and the reason we do this is that the human ear is sensitive to a very wide range of intensities. All right, 10 to the minus 12 is about the threshold of human hearing. But we can hear sounds that are all the way up. Clearly this is the lower limit, but we're okay with sounds that are all the way up to 10 to the minus 3, 10 to the minus 2 watts per square meter without damaging our ears. So that's like 10 decades of intensities. That's just a very large range. By taking a logarithm, we make a very large range into a very manageable range. Alright, so what we're asking for is the change in sound level. How does the sound level change when we increase or decrease the intensity by these factors? So it's useful to write down a second equation. If we take the difference of two sound levels, we can play with the logarithms here and come up with this equation, that the difference in the two sound levels for beta 2 minus beta 1 is 10 decibels times a log base 10 of the ratio of the intensities. Alright, that's the magic of logarithms, that it can take a division problem and make it a subtraction problem. Right, that's the way that slide rules work. Right, so for letter A here, we're told that we want to compare, or really we're asked, how does the sound level change when the sound is twice as intense? So we're saying the ratio I2 to I1 is 2. Right? I2 is twice I1, so this ratio is 2. So I can just plug this in. Beta 2 minus beta 1 is our original, that's 90 decibels, equals 10 decibels times log of I2 over I1, which is simply 2. Alright, so if you do the right-hand side here, what you get is that is 3 decibels. Right, so then you add this 90 to the other side, and what you get is that beta 2 is 93 decibels. Alright, so our intensity has increased by a factor of 2, but the sound level has only increased by 3. Right? 3 versus the 90 that it started at. Again, we're just trying to take a very broad range of intensities and bring it into a manageable range of sound levels. So for letter B, we're told that the ratio of intensities is now 1/5, right? So we've decreased our intensity by a factor of 5. So we'll do the same kind of math. Beta 2 minus 90 decibels equals 10 decibels times a logarithm of 1/5. Alright, that logarithm is actually negative, right? So that gives us minus 6.99 decibels. And if you add 90 to both sides, what you get is beta 2 is 83 decibels. Okay, the second problem is this. An 8-hour exposure to a sound intensity level of 90 decibels may cause hearing damage. Right? The question is, what energy in joules falls on a a 0.8 centimeter diameter eardrum that's exposed for 8 hours to 90 decibels of sound. So let's write down some things that we're given. The time here is 8 hours. Let's convert that to SI units. If you multiply by 3,600 seconds per hour, that's 28,800 seconds. Right? We're given a sound level, this 90 decibels. And we're given a diameter for the ear, which is 0.8 centimeters or 0.008 meters. Okay, so the question, again, is asking for an energy. Well, if we think about what's happening here, we have some source of sound, right? And it's emitting sound, and the intensity of the sound drops off as a function of distance. Right? So at some distance we have 90 decibels, or some intensity here. Right? So we can get an intensity from the sound level. Right? But intensity is also equal to power divided by area. Right? So if I know an intensity, I could get to a power from that. Right? So I should also think power is energy divided by an amount of time that it takes to deliver that energy. So if I knew the power, then I could get the energy, and that's what I'm solving for. Right? Ultimately, I'd like to know this energy. Okay, so we'll start by asking, what is the intensity? Well, I just need to take the definition of sound level and solve it for I. Right? The equation we get there is I equals 10 to the minus 12 watts per square meter, right, times 10 to the beta over 10 decibels. All right, that's just what I get when I turn the equation that I gave in the previous problem around, right? Solve that for I. So just plugging into that, 10 to the minus 12 watts per square meter times 10 to the 90 over 10. Right? So what I have here is 10 to the minus 12 times 10 to the 9, right? Which becomes 10 to the minus 3, right? Or I'll just write it as 0.001 watts per square meter. So that's my intensity. Now I should ask, what is the power falling on an eardrum with some area? Right? So power, is pretty simple. P equals I times A. So intensity was 0.01 watts per square meter, and the area is pi r squared. R is 0.004 meters squared. So the power here is 5.03 times 10 to the minus 8 watts. Okay, and then finally I could ask, what's the energy? So energy is power times time. So it's going to be this 5 times 10 to the minus 8 watts times 28,800 seconds. And what I get is 1.45 times 10 to the minus 3 joules. Put a little box around that. Which doesn't seem like a lot of energy, but it's not an amount of energy that you would want to be falling on your eardrum, right? Because your eardrum is very small and very delicate.